Okay, we've noted that this matrix, which we call A, is symmetric. Now we ignore the process by which we obtained this matrix, and let's see if we come full circle by finding a set of eigenvalues and eigenvectors that match this set. Okay, to find the eigenvalues, and we talked a lot about why you have to know what each step means and why each step is important and how it reflects the basic questions and basic definitions of an eigenvector. But the process is fairly simple. We take the determinant of the matrix A minus lambda I, where lambda is an unknown, and set it equal to 0. Now we'll come back and talk about the reasons why we do that, but that is the process. Now you're going to have to know the reasons as well as the process, but if you know the process alone, you can get by. If you want to do well, you're going to have to tell me why this process works. So kind of keep that in mind. Anyhow, just doing the process, well, as you see on the daily worksheet, I claim that this is the matrix A minus lambda I, and that's very easy to verify. You're just going to be subtracting lambda from all of the diagonal elements, and that's what you get. Again, you have to understand that in a little more depth, but that's the way it comes out. We take this determinant and we get our characteristic equation, which we set equal to 0, and we solve. I gave you the hint in the problem that lambda equals 1 is one of your eigenvalues, one of the solutions to this equation. If you then do a long division or synthetic division, divide this polynomial by lambda minus 1, you'll end up with the quadratic polynomial lambda squared plus lambda minus 6, okay, which factors into lambda plus 3 times lambda minus 2, giving you solutions 1 and 2, as well as negative 3 and 2, as well as the solution 1 that we already had. And you do need to understand how to solve polynomial of degree higher than 2 if you can find one or more of the roots. Okay. This is what we get. And now what do we do? Well, the procedure is we plug in lambda equals negative 3 and reduce the matrix. Now, the matrix equation that we're representing by this matrix is the equation, if we put in negative 3 here and get our numbers and our fractions and stuff, it's that matrix times the eigenvector x1, x2, x3 equal to 0. Okay, we know that we can solve that equation for x1, x2, x3 by simply reducing the matrix and interpreting this as saying x1 plus 0, x2 plus x3 equals 0, which is what we have here. 0x1 plus x2 minus 2x3 equals 0. Well, that's x2 minus 2x3 equals 0. And the third line just tells us that 0 equals 0. If the third line told us anything else about 0, that it was equal to something else, it would be false. Or we would get, well, from the fact that 0 automatically equals 0, we conclude that one of our variables can be treated as a free variable. We choose to treat x3 as a free variable. I'm not going to explain all details of that because we'll lose the thread of what we're doing here. But this matrix applied to this vector means that we have this, and that our vector then, our eigenvector, is x3 times negative 1, 2, 1, where x3 could be any number except 0. Okay, so now negative 1, 2, 1 is an eigenvector, and it should have eigenvalue negative 3. Well, you can, if you wish, multiply negative 1, 2, 1 on the left by this matrix, and you're going to get negative 3 times this. That would be 3, negative 6, negative 3. If you multiply this vector on the left by this matrix, you're going to get 3, negative 6, negative 3. Now, if lambda equals 1, well, we do the same thing. The matrix reduces to this, and I haven't written out the equations. This means x1 plus x3 is 0, x2 plus x3 is 0, so that whatever x3 is, x1 is going to be the negative of x3, and so is x2. So if we just let x3 equal 1, x1 and x2 both have to be negative 1. And then this is our eigenvector with eigenvalue 1. Okay, if you multiply the matrix here by this vector, you just get 1 times this vector. You get this vector back. And similarly for lambda equals 2, we get this eigenvector. Eigenvalue is 2. You can check it out. Multiply matrix on the left by this. You're going to get 2 times this. You're going to get 2, 0, 2. So we find 3 eigenvectors. Now we have a set of eigenvectors. Is that an orthonormal set? Well, let's check the ortho part at least. If we take the dot product of this with this, negative 1 times negative 1 is 1, negative 1 times 2 is negative 1, 1 times 1 is 1, we got 1, negative 2, 1 adds up to 0. Okay? This dotted with this, we get negative 1 and 0 and 1, which adds up to 0. This vector dotted with this vector gives us negative 1, 0, 1, adds up to 0. So this is an orthogonal set. And it's worth noting that if this matrix is symmetric, these matrices, or these eigenvectors, will be orthogonal. So a symmetric matrix implies orthogonal eigenvectors. Now, is the set orthonormal? Well, each of these eigenvectors has a 1 in it. And each has something else in it that isn't 0. So clearly its magnitude is bigger than 1. Now we could calculate the magnitudes. The magnitude of this one is 1 squared plus 2 squared plus 1 square root thereof. That's a square root of 6. This one has magnitude square root of 3. This one has magnitude square root of 2. So can we somehow get an orthonormal set out of these 3 vectors? Well, we'll do that in the next video.